Let's start with 4, our electrodynamic fields. You can see the background of the PPT, am I right?
Yes, sir.
Wavy in the nature. So our fields now, not the agriculture fields, but electric field and magnetic fields are no more steady or stationary. We don't have any stationary charge sitting at one place and radiating its electric field. We really don't have steady magnetic fields generated by some horseshoe magnet. We have the magnetic fields generated by the electromagnetics, okay, probably generated using AC currents. Yeah. So everything is now changing and everything is waving. They have some kind of um, different behavior compared to the static nature. Those are now dynamic. So if I say that charge is really not exhibiting a constant value and its value is keeps on changing, therefore its radiated electric field will also keeps on changing. You can visualize a bulb with light fluctuations. So you will have the changes in the light intensity. Am I right? So how we define the changes in the light intensity from a bulb? We observe the light intensity at, let us say, t is equal to 1 second. Then at t is equal to 2 seconds, if we find the difference in the light intensity, yes, we say that light intensity has changed. Similarly, we try to observe the light intensity at different time intervals, and if those values, numerical values, are different, so we can say that okay, the light emitting from the bulb is time dependent. It changes with respect to time. And whenever we do have a word, something changes with respect to time, we do have d by dt representation in the mathematics. Okay, so till unit number 1, we studied about static fields generated due to your charges or maybe due to currents. Okay, the fields were not dynamic, the fields were static, the fields intensity were not changing with respect to time. And now in this unit number 4, we want to give that time behavior, we want to analyze that time behavior of the fields. Okay, so for syllabus we do have Faraday's law, which talks about the translation and motional EMF, which already was studied as a part of physics. Then new point, displacement current, which tries to explain how current flows through dielectrics. We know how electric field flows through the dielectrics. We do have a concept of polarization over there. इलेक्ट्रिक फील्ड की वजह से वहाँ पे पोलराइजेशन होता है, and we know how electric field propagates through it. But how really current passes through the capacitor, we really don't know. And for the matter of fact, displacement current over here is still a theory. Okay, it is still a theory. There are groups who believes in displacement current theory, and there are another groups we really who really don't believe in displacement current theory. Some of the groups do believe that okay, we do have ether as a material in our space. You can think about how energy is being radiated from the sun to the earth. There we don't have any dielectric material, we don't have any sort of material. What we have? Empty space, we have vacuum over there. Still we are able to get the energy from the sun. So there are some groups who believe that okay, space is not empty, there is certain material, and that material exhibits certain properties, and it is called as ether. Once again, theory. So displacement current point over here is actually still a theory which has been proved mathematically, but no experimental observations, or I will say that results, were observed. So displacement current we are going to see as an adjustment. How we will see? Then time varying Maxwell equations, whatever equations we have seen till moment. In the starting lectures, I told you that Maxwell, sorry, Maxwell tried to concise all the mathematical findings. Okay, all the mathematical findings of 300, 400 years together, and he fit all the equations with mathematical adjustments in between them. So it was not easy task to put the electric field equations and magnetic field equations in together and tell mathematically that okay, these equations are having some connections. Okay, the joining the two distinct fields of study. Okay, till till the starting of 19th century, it was assumed that electric fields are completely different, whereas magnetic fields are completely different, and they don't have any relation in between them. Okay, so Maxwell put all the mathematical equations together and told that no, those are not independent, but those are dependent. Okay, so we do have some point form, that is differential form and integral forms of the Maxwell's equation. Then we do have power and Ponting theorem. Okay, so it talks about how much power is being radiated and how much power is being lost during the transmission of electromagnetic field. For an example, let us say an antenna and radio antenna radiates electric field, and it do have some losses in the atmosphere. So it talks about those losses. And then we have the concept of retarded magnetic vector potential. Okay? This is the syllabus, and surprisingly we really could end unit number 4 within a span of 1 hour, but really we do not have that much amount of time for our lecture, so we may extend the part of unit number 4 in tomorrow's session as well. So going with Faraday's law, okay, something got stuck. So we do have concept number 1. Okay, the magnetic field produced by a changing electric field. It is called as Ampere's law. Okay, then we do have another observation: electric field produced by changing magnetic field. Okay? So I can say that okay, that was a experimental findings of the Michael Faraday. The the two different laws found by two different people in different timings. Okay, probably in a gap of 50 to 60 years, but they do have some thin connection together. So we are going to study a Faraday's law, which talks about okay, electric field is produced by the changing magnetic field. You probably remember horseshoe magnet experiment, which you have studied in school timings. So we do have North Pole and South Pole, and actually we do have some electric flux lines in the North and South Pole, in between the North and South Pole. We keep a coil, okay? We keep a coil in between in the magnetic field, and we know that if this magnetic field and the coil, both of them are stationary, no current will be produced. Sorry. And if we say that okay, the coil or loop is stationary and B bar generated by the horseshoe magnet is varying, then we say that okay, there will be certain amount of current will be generated. In opposite way, if the loop or the coil is rotating, okay, if the coil is rotating, so we can say that even if magnetic field is not changing with respect to time, still we will have certain amount of current generated in the coil. Okay, I is equal to integral b bar dot ds bar. And if we have the coil or the loop as well as magnetic field, both of them are varying, So definitely we will have the certain amount of current generated into the coil, which is it is also called as dynamo. Okay. So Faraday generated this kind of experimental setup somewhere 150 years ago, which we are studying in school days now. So Faraday's law, it told that the electromagnetic force, electromotive force, which has been generated inside the coil, it is actually due to rate of change of magnetic flux intensity phi, rate of change of magnetic flux lines phi, and this negative sign indicates that the resultant current is actually opposing the resultant current is actually opposing the force which has created it. Okay, तो दोनों भी चीजें हैं कि भाई EMF जनरेट हो रहा है, it is in the opposite direction to the magnetic field, therefore negative sign, and it is generated due to changing magnetic flux lines. ये Faraday's equation था basic. So negative sign indicates that produced EMF opposes the rate of change of flux which creates it. Okay, which creates EMF. Then magnetic flux density, we know that B bar is equal to magnetic flux lines phi upon S. So since we are looking at the ratio, we can write down d phi by ds. Okay. So therefore, d phi, rearranging the terms, d phi is equal to b bar dot ds bar, and we can say that okay, the total number of magnetic flux lines is equal to closed surface integration. Your loop is a closed loop. It necessarily needs to be a closed, otherwise we cannot generate a current into that. So closed surface integration of b bar dot ds bar, and we had an equation EMF is equal to minus d phi by dt. Put a value of phi over here. Okay. Therefore, we will have we will have EMF is equal to minus d bar by dt integration closed surface integration of b bar dot ds bar. Take this integral inside the take this differentiation inside the integral sign. Outside it is d by dt. When we are taking it inside the integral, it will become partial differentiation, and we will have minus closed surface integration of dabba d bar by dabba t dot ds bar. Okay, so we have some mathematical arrangement over here, but still we are talking about the Faraday's law only. It is still a Faraday's law expressed mathematically in a different way. Voltage generated is also given as EMF is equal to closed line closed loop integration of E bar dot DL bar. Okay, EMF generated is equal to closed loop integration of E bar dot DL bar. So we can say that closed loop integration of E bar dot DL bar is equal to minus closed surface integration of dabba B bar by dabba T dot DS bar. Since both the sides, both the left hand sides were equal, we can say that okay, right hand sides will be equal. This is similar to transformer equation. I can say that inside a transformer, we do have primary windings as well as secondary windings, and how magnetic flux linkage happens in between the two windings. First point, both windings are closed loop in nature. So whenever we do have some sort of electric field or potential applied to closed loop lines, it is going to generate your magnetic field. This is the basis of your transformer equation. Now moving on to next, the case one, which where we were talking about the loop is stationary and B bar changes with respect to time. So we can say that EMF produced inside the loop will follow this equation, minus of closed surface integration of d dabba B bar by dabba T dot ds bar. It is a transformer induction equation, just we said. This is also called as the Maxwell equation, which was derived from the Faraday's law. Faraday did not talk about the magnetic flux density. Faraday did not talk about the differential surface area. All those mathematical adjustments were done by the Maxwell. In case 2, B bar is stationary and the loop is rotating with certain velocity V bar. So we will have a loop generated EMF. EMF is equal to closed loop integration of E bar dot DL bar. Then according to Lorentz force equation, probably you may recall from the physics, a force exerted, look at the equation, a force exerted on a charge moving with certain velocity v inside a magnetic field density b bar, okay, is given by this expression. This is once again an experimental formula that is called as empirical formula. Force exerted on a point charge which is moving with certain velocity v bar inside a magnetic field b bar. What amount of force? So this much amount of force will be exerted on that point charge. This is the Lorentz force. So we know that electric field intensity is equal to F bar upon Q. So we can take this Q on the left hand side and we will be left with cross product in between the velocity of the charge and the magnetic field through which that charge is moving. So we can modify this equation. So we will have EMF is equal to closed loop integration of V bar cross B bar dot DL bar. So this is an EMF equation if B bar is stationary and your loop is rotating with certain velocity. Okay, loop is rotating with certain velocity. Then case 3, loop is rotating as well as B bar is changing. So we can say that here B bar was changing, here loop is varying. So we can say that if both of them are varying, we can add the equation number 1 and 2 and we will have the EMF generated due to both conditions as closed loop integration of V bar cross B bar dot DL bar. Minus sign becomes as it is, okay, it is from the equation itself, otherwise we would have gone for plus sign, but since minus sign we will have minus sign over here. Closed surface integration dabba b bar by dabba t dot ds bar. Straightforward application of the Faraday's law which was mathematically applied by the Maxwell. Sorry. So let us look at two numerical based on the Faraday law. A circular loop, why we are looking at the numerical, because this can be asked as a MCQ. A circular loop conductor having radius r, okay, radius दिया हुआ है, is placed in xy plane, that is z is equal to 0 plane. The loop has resistance, okay, resistance r दिया है. If b bar has certain equation, we really do not read equation at all. B bar is given by certain expression, okay, fine. Calculate the current passing through the loop. अभी current passing through the loop, we know that I is equal to V by R and we need to calculate V, that is EMF. How much EMF has been generated inside the circular loop. So we do have a relation. EMF is equal to minus d by dt of closed surface integration of B bar dot ds bar. The loop is placed in xy plane. Okay, therefore its surface area will have the normal component as an cap is equal to az cap. Okay, क्योंकि loop कहाँ पे रखा है xy plane में. Okay, so if we have xyz and we have a loop over here, only one normal component will be along the az direction. This is the perpendicular direction. So we can say that okay, EMF is equal to minus d by dt closed surface integration of, यहाँ पे लिख दिया b bar का equation which was having az cap और यहाँ पे लिख दिया ds bar का equation that is your ds az cap. So we will have minus d by dt, take out all the constant values. इतनी जो constant values है इसको बाहर निकाल लीजिए. az dot az was 1, so closed surface integration of ds. Okay, so that the closed surface integration of ds, that is nothing but area of circle. Okay, this is a circular loop, so we have placed the pi r square for this integral. Okay. So we do have some differentiations to be done over here with respect to time, and rest of the quantities will be constant. So we will have, okay, the same equation has been rewritten. So we will have 0.5 pi r square as a constant, but we will differentiate this sine 10 raised to 3t. So minus sign as it is, 0.5 pi r square as it is. The derivative of sine 10 raised to 3 is cos 10 raised to 3t, and this 10 raised to 3t comes extra because we know that d by dt of sine of at is equal to A cos of AT. That this A is 10 raised to 3 in our case. So we do have calculations minus 335.34 cos of 10 raised to 3 T. Okay, you can observe here the EMF generated is time dependent. It is going to vary with respect to time. And if you observe a cosine waveform, for an example, nothing to do with the mathematics, if you observe the cosine waveform, you do have this kind of nature. Okay, so we do have some voltage and we do have the time axis. It keeps on changing its value with respect to time. And now definitely we can calculate the current I, that is EMF upon R. So EMF has an equation minus 35.34 cos of 10 raised to 3t upon 20 ohm. Okay, so we will write down amperes. This will be current. Going to the next numerical, an area
सर
of,
एक मिनिट तरी लास्ट वाला दाखवा ना एक
yes,
मिनिट यस सर
an area, यहाँ पे area ही दिया हुआ है आपको. In Z is equal to 0 plane, means once again it is in the XY plane and it will have AZ as a normal component or a perpendicular component. Encloses a filamentary conductor. Find induced voltage, that is EMF, if B bar is given with certain expression. कुछ भी expression रहने दो. Okay, what we need to do? We need to do the dot product. So EMF has this relation minus d bar by dt, closed surface integration of B bar dot ds bar. So we can say that, okay, fine. Since ds bar is equal to az cap, okay, so this ay component is going to vanish because we know that ay dot az will result in 0, whereas az dot az will result in 1. So we have made some shortcut over here. So we will have b and we will have the closed surface integration of ds. इसका value आपको दिया है 0.65, okay, and b we will have 0.05 cos of 10 raised to 3t upon root 2. तो ये वैल्यू b की यहाँ पे लिख दी और s की वैल्यू भी लिख दी. Okay, we really don't have any vectors over here after doing the dot product, so we do have the expression and we need to do the differentiation as well. Okay, how we can do this? I will write down over here minus 0.05 into 0.65 upon root 2 d by dt cos of 10 raised to 3 t. So this is nothing but minus the bracket as it is. You can do the calculations. Cos का डेरिवेटिव क्या होता है? माइनस साइन. ओके, माइनस साइन 10 raised to 3t along with 10 raised to 3. यहाँ पे वो 10 raised to 3 रह गया लिखना. So this minus sign and this minus sign got dissolved and we have the bracket and sine of 10 raised to 3 t into 10 raised to 3 volt. We have calculated the EMF. So volt must be the unit of an EMF. Okay. So whatever let it be the formula expression for B bar, you have to just put the values in the expression of EMF. Okay, probably you have done this one in physics also. Then we want to go for next relation, which tells about how electric field and magnetic fields are related to each other. So we know that one equation tells us about what if the electric field is changing or the loop is rotating and B bar was stationary. So EMF generated was closed loop integration of E bar dot dl bar is equal to minus closed surface integration of d bar dot db bar dabba b bar bar dabba t dot ds bar. ये relation है. Applying Stokes theorem. If you remember, the Stokes theorem was relating the line integral and the surface integral. So E bar dot dl bar, which can be expressed as curl of the E bar observed over the closed surface. Okay, and we know that this integral is equal to this integral. So we can say that, okay, this is also equal to this one. So we can say that both the sides, on both the sides we do have a surface integration, so we can relate the terms individually. So curl of E bar dot ds bar is equal to minus dabba b bar by dabba t dot ds bar. So on the both sides we do have ds bar, so cancelling out. So we will relate with, okay, the curl of electric field is equal to minus dabba b bar by dabba t. Okay, this is very important relation which was not observed for almost 300 years. Okay, ये relation observe नहीं हुआ था. No one talked about mathematical relation in between the two. Yes, indeed, in some years the mathematicians and physicists talk about there might be some relation, but what relation we really don't know. If you go with the historical notes from the Faradays or Gauss, they always talk about we found a behavior, but we do not understand. We cannot express it mathematically. They admitted it, but after a discovery of lots of physical experiments and lots of mathematical advantages, this relation proved that, okay, there is relation between the electric fields and the magnetic fields, and those really are not independent of each other. Okay, and therefore it is called as the Maxwell's equation in point form or differential form. Whenever we do have dabba by dabba t or certain kind of differential equations, or we do have the nabla or delta in the equation, it is called as point form or differential form. Okay, one moment please.
सर तुम्ही म्यूट आहात.
Yes, 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 I am on mute. Actually, we had an announcement to make over here. Mm, and I was adding Saurabh sir in our, what we say that, in our meeting, in our class. One moment, please. Okay, I am really afraid that whether he is able to join our meeting or not. I have sent him an invitation for that. Let us see how he can join. Let us see. No, I guess he is out of net. Okay, no worries. So we have certain relation with the electric fields and magnetic fields now. Okay, and here is a discussion about the displacement current, which I will explain in next session. Okay, and we will try hard to get our Saurabh sir into the meeting. I will stop the recording now.